Templates are a feature of the C++ programming language that allows functions and classes to operate with generic types. This allows a function or class to work on many different data types without being rewritten for each one. Templates are of great utility to programmers in C++, especially when combined with multiple inheritance and operator overloading. The C++ standard library provides many useful functions within a framework of connected templates. Major inspirations for C++ templates were the parametrized modules provided by CLU and the generics provided by Ada. Technical overview. There are three kinds of templates: function templates, class templates, and, since C++ 14, variable templates. Since C++ 11, templates may be either variadic or non-variadic. In earlier versions of C++, they are always non-variadic. Function templates. A function template behaves like a function except that the template can have arguments of many different types. In other words, a function template represents a family of functions. The format for declaring function templates with type parameters is template less than class identifier greater than function underscore declaration, template less than type name identifier greater than function underscore declaration. Both expressions have the same meaning and behave in exactly the same way. The latter form was introduced to avoid confusion, since a type parameter need not be a class. For example, the C++ standard library contains the function template max, which returns the larger of x and y. That function template could be defined like this: template less than type name type greater than type max, return a greater than b, a, b. This single function definition works with many data types. The usage of a function template saves space in the source code file in addition to limiting changes to one function description and making the code easier to read. A template does not produce smaller object code, though, compared to writing separate functions for all the different data types used in a specific program. For example, if a program uses both an int and a double version of the max that operates on int arguments and another object code version that operates on double arguments, the compiler output will be identical to what would have been produced if the source code had contained two separate non-templated versions of max. This will call max less than int greater than by implicit argument deduction. std cout less than max less than std endl. This will call max less than double greater than by implicit argument deduction. std cout less than max less than std endl. This depends on the compiler. Some compilers handle this by defining a template function like double max less than double greater than, while in some compilers, we need to explicitly cast it, like std cout less than max less than double greater than, std cout less than max less than std endl, std cout less than max less than double greater than std endl, return 0. In the first two cases, the template argument type is automatically deduced by the compiler to be int and double, respectively. In the third case, automatic deduction of max would fail because the type of the parameters must in general match the template arguments exactly. Therefore, we explicitly instantiate the double version with max less than double greater than must be overloaded in the type. Class templates. A class template provides a specification for generating classes based on parameters. Class templates are generally used to implement containers. A class template is instantiated by passing a given set of types to it as template arguments. The C++ standard library contains many class templates, in particular the containers adapted from the standard template library, such as vector. Variable templates. In C++ 14, templates can be also used for variables, as in the following example. template less than type name t greater than const expert t pi equals t. Template specialization when a function or class is instantiated from a template. A specialization of that template is created by the compiler for the set of arguments used, and the specialization is referred to as being a generated specialization. Explicit template specialization. Sometimes the programmer may decide to implement a special version of a function for a given set of template type arguments, which is called an explicit specialization. In this way, certain template types can have a specialized implementation that is optimized for the type or more meaningful implementation than the generic implementation. If a class template is specialized by a subset of its parameters, it is called partial template specialization. If all of the parameters are specialized, it is a full specialization. Explicit specialization is used when the behavior of a function or class for particular choices of the template parameters must deviate from the generic behavior, that is, from the code generated by the main template, or templates. For example, the template definition below defines a specific implementation of max, return A, B, variadic templates. C++11 introduced variadic templates, which can take a variable number of arguments in a manner somewhat similar to variadic functions such as std, print. Both function templates and class templates can be variadic. Advantages and disadvantages of templates over macros. Some uses of templates, such as the max macro that evaluates to the maximum of its two arguments, as defined by the less than operator. #define max less than. Both macros and templates are expanded at compile time. Macros are always expanded inline, while templates are only expanded inline when the compiler deems it appropriate. When expanded inline, macro functions and function templates have no extraneous runtime overhead. Template functions with many lines of code will incur runtime overhead when they are not expanded inline, but the reduction in code size may help the code to load from disk more quickly or fit within RAM caches. Macro arguments are not evaluated prior to expansion. The expression using a macro defined above max 100 may evaluate to a negative number, while the call to template function std, max 100, will always evaluate to a non-negative number. As opposed to macros, templates are considered type safe, that is, they require type checking at compile time. Hence, the compiler can determine at compile time whether the type associated with a template definition can perform all of the functions required by that template definition. By design, templates can be utilized in very complex problem spaces, whereas macros are substantially more limited. There are fundamental drawbacks to the use of templates. Historically, some compilers exhibited poor support for templates. So, the use of templates could decrease code portability. Many compilers lack clear instructions when they detect a template definition error. This can increase the effort of developing templates, and has prompted the development of concepts for possible inclusion in a future C++ standard. Since the compiler generates additional code for each template type, indiscriminate use of templates can lead to code bloat, resulting in larger executables. Because a template by its nature exposes its implementation, injudicious use in large systems can lead to longer build times. It can be difficult to debug code that is developed using templates. Since the compiler replaces the templates, it becomes difficult for the debugger to locate the code at runtime. Templates of templates are not supported by all compilers, or might have a limit on the nesting level. Templates are in the headers, which require a complete rebuild of all project pieces when changes are made. No information hiding. All code is exposed in a header file. No one library can solely contain the code. Additionally, the use of the less than and greater than signs as delimiters is problematic for tools which analyze source code syntactically. It is difficult for such tools to determine whether a use of these tokens is as comparison operators or template delimiters. For example, this line of code, foo, may be a function call with two parameters, each the result of a comparison expression. Alternatively, it could be a declaration of a constructor for class foo taking a parameter d whose type is the parameterized a less than b, c greater than. Generic programming features in other languages. Initially, the concept of templates was not included in some languages, such as Java and C#1.0. Java's adoption of generics mimics the behavior of templates, but is technically different. C# added generics in .NET 2.0. The generics in Ada predates C++ templates. Although C++ templates, Java generics, and .NET generics are often considered similar, generics only mimic the basic behavior of C++ templates. Some of the advanced template features utilized by libraries such as Boost and Sourcesoft, and implementations of the SGL itself, for template metaprogramming are not available with generics. In C++ templates, compile time cases were historically performed by pattern matching over the template arguments, so e.g., the below factorial template space case is implemented by matching 0 rather than with an inequality test, which was hitherto unavailable. However, the arrival in C++ 11 of standard library features such as std conditional has provided another, more flexible way to handle conditional template instantiation. Induction template less than int n greater than struct factorial, static constant value equals n asterisk factorial less than n1 greater than value, base case via template specialization. Template less than greater than struct factorial less than 0 greater than static constant value equals 1. With these definitions, one can compute, say 6, at compile time using the expression factorial less than 6 greater than value. Alternatively, constexpr in C++ 11 can be used to calculate such values directly using a function at compile time.